Welcome to the 8th lecture in Riparian Function and Management. In our last meeting, we examined Lane's balance and the relationship between water and sediment with a stream channel. You will recall that Lane's equation has 4 variables, including QS, it's the sediment load, and D50, meaning the sediment size. QW is stream flow at bank full, and S is channel slope. We discussed how the water side represents energy generation and the sediment side, energy dissipation. We saw examples of the power-hungry water eating away at stream beds and banks. We examined degradation, erosion, and aggradation deposition, and how a stream rebalances its water and sediment to balance the equation. In this lesson, we will examine the role of vegetation in riparian function and recovery. Vegetation was not included in Lane's equation. All energy dissipation was a function of sediment size and channel slope. In reality, vegetation plays an enormous role in both recovery and stability. Vegetation helps to buffer dramatic swings in the water-sediment balance. Erosion and deposition will still occur in a well-vegetated riparian area, but their magnitude and extent are mitigated by the energy dissipation provided by strong-rooted, dense vegetation. Vegetation also plays a large role in riparian water storage, as fine sediments containing organic matter are trapped and held, and the water holding capacity is enhanced. You will recall our definition of functioning condition involves having enough stuff, vegetation, landform, or large woody material to first and foremost dissipate stream energy. And so it is physical function that produces the values that we appreciate and demand from our creeks and our rivers. Note, key terms in this description are banks, erosion, sediment, and flow. The third leg of the triangle we discussed earlier is vegetation. This is actually the one side of the triangle that we have the most influence over and the ability to manage directly. Even though these two terms can mean the exact same thing when it comes to grammatical definition, they can also be interpreted to mean exactly the opposite of each other when it comes to functioning of the water cycle. So watershed and water catchment. What are the differences? Well, one of the big differences, and maybe the biggest visual difference between a watershed and a water catchment, can be seen in the vegetation. Here's the difference. Here you can see what a watershed is. And this side of the fence is more of a water catchment. So if you ask yourself the question, are your lands functioning more as a watershed, or are they functioning more as a water catchment? The most visible difference is going to be the presence, abundance, density, health types, and vegetation present. As with the uplands, watershed and water catchment previously pictured, the main difference between functional and dysfunctional riparian areas can be evaluated by observing the vegetation. Pictured here are images of functional and dysfunctional riparian areas from across Texas. This dysfunctional riparian area has zone characteristics which include exposed soil or gravel on the banks and in the floodplain, a wide channel with shallow water, increased flood flows, and excessive erosion often resulting in stream bank collapse. Other signs of a degraded riparian system are lack of shade or lack of overhanging vegetation and the absence of large wood or downed trees in the stream bed. This results in the loss of value production like fish and wildlife habitat. Now, when we look at creeks like this one, you are likely beginning to see what might be missing. You might be able to see what the riparian could be capable of looking like if given the opportunity to recover. The original Lane's balance does not consider riparian vegetation or account for the roughness and energy that it dissipates. The upper Nueces is beginning to rebalance its sediment load, and that recovery can be mostly attributed to a recovery of stabilizing riparian vegetation. We will visit this site during one of our class field trips. Riparian plants are generally divided into 5 categories: sedges and rushes, grasses, woody plants, forbs, and ferns and vines. No single type is better or preferable to another. For example, some riparian areas are highly functional without woody plants, yet others are almost entirely made of woody plants and large trees. As Steve Nell said, there is no greater social or political, or as Steve Nelly said, there is no greater social or political or economic or biological issue in Texas than water. Many folks have put their water hopes in such grandiose plans as reservoirs, interbasin transfers, pipeline projects, brush control, desalinization, and other such solutions. Yet, there's another large and mostly unrecognizable source of water that can be developed in nearly any part of the state. So one of the attributes of a properly functioning riparian area is the sponge effect and the water storage capacity within the riparian area. This does not refer to water storage in the creek channel itself, but water detention in the land. The large absorbent sponge of a riparian land will soak up, store, and then slowly release water over a prolonged period. This riparian sponge can be managed in a way to greatly increase and improve this storage, or it can be managed in a way to decrease and degrade water storage. The key to building a bigger and better riparian sponge all begins with the right kinds and amounts of vegetation. The vegetation growing within a riparian area can indicate the presence or absence of a groundwater connection, the key indicator of perennial flow. A wetland indicator, seen here as WI, status, is assigned to plants according to the degree of soil moisture needed and tolerated by the plant. This rating is based on the U.S. Fish and Wildlife Service's wetland plant list compiled in 1988, with numerous revisions. WI, or Wetland Indicator Status, varies somewhat between regions within the United States. This field guide uses a 2014 U.S. Army Corps of Engineers Regional Wetland Plant List for the Great Plains region, which includes most of Texas. There are 5 wetland indicator categories. You have OBL, obligate wetland plants, which are almost always found in wet locations. Also, you have FACW, facultative wetland plants, or FAC-wet, usually found in wet locations. There are FAC, or facultative plants, found equally in wet and dry, non-wet locations. There are FACU, or facultative upland plants. These are usually found in dry, non-wet plant locations. And last, there are UPL, or upland plants, which are almost always found in dry, non-wet locations. An abundance of OBL, obligate, and FACW, facultative wet plants, indicates that the riparian area is storing water and maintaining a water table connection for much of the year. The condition is sometimes referred to as a riparian sponge. Likewise, a riparian area lacking the OBL, or obligate, and FAC-wet plants indicates that the riparian area is not storing water very effectively. This can be a sign of groundwater table decline. There is evidence water is being stored in this bank and floodplain because the plant growing there indicate wet conditions. Among the plants pictured here are some strong obligate and facultative wet, or FAC-wet, plants. First, we see an obvious obligate plant. This is watercress growing in the water. Then note the emery sedge on the bank. This also is an obligate plant. And away from the visible water and the floodplain, we can find black willow, a facultative wet plant. Observe this photo. There is no water storage indicated in this bank or floodplain because the plants growing here do not require wet conditions. Live oak is a facultative upland or FAC-U tree, and KR bluestem is an upland known as a UPL grass. A stability rating, or SR, is assigned to riparian plants according to the plant's observed ability to withstand erosive forces of water in most of Texas. The rating scale is 1 to 10. The SR1 is equal to bare ground. An SR10 would be the strength of an anchored rock. An SR6 or 7 has the minimum strength required for bank stabilization. Each picture here is seriously lacking vegetative cover. Mostly, you're going to see bare ground. In the photo at the lower right, there are plants on the bank, but they're upland plants and they're in an unhealthy condition. Bare ground has a stability rating of 1. There are no signs of a riparian sponge indicated anywhere. A plant with an SR10 has the reinforcement strength and the stability of an anchored rock, but better. Stability is very important for holding sediments and banks together during high-energy flood events. Bald cypress, the largest and most characteristic riparian tree, is found on many steep gradient creeks and rivers in the Texas Hill Country. It has a stability rating of 10, which, as we discussed, is equivalent to anchored rock. The woody roots of cypress form an exceptionally strong bulwark of reinforcement along the banks, which effectively resists the flash flooding common in the area. Fine feeder roots also aid in holding these loose soils together. Like all trees, cypress can give way in a flood or die from drought, and when they do, they form important large dead wood in the channel or floodplain. This plays an extremely important role in initiating and sustaining riparian stability. Large, strong trees are not the lone vegetation type to play an enormous role in stabilizing the riparian setting. Sawgrass, a large sedge, also has a stability rating of 10. It has a strong stabilizing root system and a large, robust top growth that effectively dissipate energy and trap sediment. That gives it one of the highest stability ratings of any riparian plant found in Texas. Here, weaker-rooted plants such as sycamore and pecan trees, both rated SR6, are fortified when their roots are interlaced with sawgrass. Together, they can create a high-stability community. Good coverage with plants having a stability rating of 6 to 7 is considered the minimum necessary for bank stabilization. Pictured here is a community of plants with a stability rating of 6 to 7. Unless reinforced by high stability species, they will probably not withstand a very large, high energy event. However, they would stay in place and hold sediments through regular and moderate flooding. Black willow has a stability of 7 and very distinctive roots. Here is saltgrass, which has a stability rating of 7 and can form extensive thick colonies of rhizomes rooting at the nodes. Cottonwood is a characteristic riparian tree in parts of Texas. It has a sufficient stability rating, especially if accompanied by a strong-rooted riparian grass or other woody plants. Riparian plants are categorized into 3 functional groups. There are pioneers. These are the plants that live where others cannot. There are colonizers, which are quick-spreading, sediment-trapping plants that put down a mat of new, delicate roots by stolons or rhizomes. And there are stabilizers, which are woody and herbaceous plants, usually tall and upright, with strong and dense root masses. Though they are slower to establish, once established, stabilizers are strong and more permanent. Pioneers live where other plants cannot. On some headwater rivers, especially in central Texas, large destabilized gravel deposits are very common. These are harsh environments for plants. They lack shade and soil, and they can have poor water holding capacity. Plants that grow on these large barren gravel deposits are very special. They are pioneers, which mostly consist of facultative and upland plants. And they aid in preparing more favorable conditions for other riparian plants to soon grow. People usually don't love pioneer plants, but they do play an essential role in riparian recovery. Some examples of pioneer riparian plants include these. You have baccharis, sycamore, Lindheimer indigo, desert willow, little walnut, burrowbush, and bricklebush. Another group of early recovery plants that are not quite as brave as pioneers we call colonizers. Colonizers are usually among the first plants to establish in freshly deposited sediments. They spread very quickly, creating a mat of new roots by stolons or rhizomes. These plants are fast growers. They trap sediment, creating niches for deeper-rooted plants to take hold. And they usually grow right at the water's edge or even out into the water. Colonizers or early stage colonizers are weak-rooted, and their main function is to spread quickly. They are critical to the recovery of riparian areas. Late stage colonizers have stronger roots but do not grow as quickly. They provide a combination of colonizer and stabilizer functions. Some early stage colonizer plants include frog fruit, a facultative SR4, water primrose, an obligate SR3, watercress, an obligate SR3, and pennywort, an obligate with a SR3. None of these have the stability to stand up to a high energy event, but they are all very good at catching and holding fine sediments and playing a very important role in making way for stronger rooted stabilizing plants. Some late stage colonizer plants with moderate stability ratings include spike rush, SR6, black sedge, SR6, knotgrass, also SR6, and bushy blue stem grass, SR6. These all have a slightly higher stability rating than the early stage and pioneers, but they still need the help of strong stabilizers to resist and dissipate flood energy. The colonizer plant, spike rush, with an SR of 6, has a tremendous ability to colonize soils with its fibrous root system. This tiny little plant is able to produce as much as 22 miles of root per cubic foot of soil. Stabilizer plants are tall, upright plants with strong, dense root masses. They are both woody and herbaceous. They're slow to establish. They're strong and permanent, and they have large, stout top growth. Woody stabilizer plants function as riparian rebar because of their large root diameter and their ability to interlace with fibrous herbaceous roots. Some examples of stabilizer plants include switchgrass with a stability rating of 9, buttonbush, an SR8, emery sedge, an SR9, and Gulf cordgrass, an SR9. Those are mixed up. Switchgrass is a facultative grass that can grow equally well in dry and wet sites. With a stability rating of 9, switchgrass is known for its fibrous root mass and roots and its ability to produce 32,000 pounds of root per area. Today's lesson introduced the role of riparian vegetation and covered plant categories, wetland indicator status, and stability ratings in functional plant groups.